Hello everybody. So today we will be entering chapter 11, which is our last chapter. So this chapter is about nuclear and particle physics. So the first subtopic is on binding energy and mass defect. Okay, so in this subtopic, you should be able to define and use the equation of mass defect, which is this one. Define and use binding energy. Determine the binding energy per nucleon. And then lastly, you have to be able to sketch and describe the graph of binding energy per nucleon against nucleon number. Okay, so let's look at the Einstein mass energy relation. So from the theory of relativity, it leads to the idea that mass is a form of energy. Okay, so mass is not just mass, it is an energy. Okay, so because of that idea, the idea leads to, we can then actually relate mass and energy with this equation here. Okay, where E is the amount of energy, M is the rest mass, and C, which is the speed of light. Okay, so we know there's several units. So the first one is the electron volt. It is a unit of energy, and it is defined as the kinetic energy gained by an electron in being accelerated by a potential difference of 1 volt. Okay, so we know that 1 electron volt is equal to 1.6 times 10 to the power of negative 19 joule. Okay, 1 mega electron volt is 1.6 times 10 to the power of negative 13 joule. Okay, and then we have the second one. We have the atomic mass unit. This one you've come across this in chemistry, if I'm not mistaken, and then it is a unit of mass. Okay, it is defined as exactly 1/12 of the mass of a neutral carbon-12 atom. Okay, so one atomic mass is equal to the mass of carbon-12 atom. So we can then equate 1U to be equal to 1.66 times 10 to the power of negative 27 kilogram. Okay, so kilogram is the SI unit. Make sure you know how to convert that, but it's actually is given in your formula sheet in PSPM lah. Okay, so one atomic mass unit can be converted into the unit of energy by using the mass energy relation. Okay, so that is in joule, 1U is equal to 1.49 times 10 to the power of negative 10 joule. In electron volt atau mega electron volt, it is 931.5 times 10 to the power of 6 electron volt per C square, ataupun untuk mega electron volt, it's this one lah. Okay, that is the unit conversion. Mass defect pula, you should know that the mass defect here, the mass of nucleus is always less than the total mass of its constituent nucleons, which is mathematically shown here. Okay, so this is the mass of proton, this one is the mass of neutron. Okay, so the difference in this mass is given by this equation here. So what is delta M? Delta M is what we call the mass defect. Okay, so the mass defect is defined as the mass difference between the total mass of the constituent nucleons and the mass of a nucleus. Okay, so the reduction in mass arises because of the act of combining the nucleons to form the nucleus causes the mass to be released, some of the masses to be released as energy. Okay, so that is why there is a reduction in mass. Okay, so some of the mass is converted ataupun is released as energy. Okay, so any attempt to separate the nucleons would involve them being given this same amount of energy, baru dorang boleh kena separate. Okay, so that energy is known as the binding energy of the nucleus. Okay, oops, okay, so that energy is known as the binding energy of the nucleus lah. Okay, so if you want to separate them, you need the same amount of binding energy. Okay, right, binding energy pula. Binding energy is defined as the energy required to separate completely all the nucleons in the nucleus. Okay, so the binding energy of this nucleus is then equal to the energy equivalent to the mass defect. Okay, so we just have to times it with the speed of light, the square of speed of light. Okay, so that is how you calculate the binding energy. Next one, nucleus stability. Okay, so nucleus is viewed as a closed packet of nucleons. Okay, there's many nucleons here. So the stability depends only on the force that exists inside this nucleus. Okay, so the forces inside the nucleus are repulsive ataupun Coulomb forces between protons, as well as the attractive forces that bind all the nucleons together in the nucleus. So basically, if this is your nucleus, there will be what we call nucleons here. So they between them there's a force. Okay, so that is known as the attractive force that bind all these nucleons together. Okay, so this attractive force is called the nuclear force. Okay, so that force is responsible for the nucleus stability. Okay, so the general properties of the nuclear force are it is an attractive force and is the strongest force in nature. Okay, and then it is a short range force, so a nucleon will only be attracted to its nearest neighborhoods in the nucleus. Okay, and then it does not depend on charge, neutrons as well as protons. Okay, so they are all the same for both. And then the nuclear force depends on the binding energy per nucleon. So a nucleus is only stable if the nuclear force is greater than the Coulomb force. Okay, so proton, the magnitude of nuclear forces untuk semua ni are the same. And then lastly, attractive force, the binding energy per nucleon of a nucleus is measured using this equation here. Okay, so A is the nucleon number lah. Okay, so this graph here is showing the graph of binding energy per nucleon against the mass number. Okay, so the value of EB over A, which is this one, will rise rapidly from 1 mega electron volt to 8 mega. I can't actually see it. Oh, okay, so it will increase from 1 mega electron volt to 8 mega electron volt with increasing mass number. Okay, so the greater the mass number, the greater the binding energy per nucleon. Okay, for the nuclei between point A, nuclei with A between 50 and 80, 50 somewhere on here and 80, this shaded region here, the nuclei in this range are very, very stable. The maximum value of the curve occurs in the vicinity of nickel. So in short, nickel and ferrum, if I'm not mistaken, has the most stable nucleus lah. Okay, and then for mass number greater than 62, the values of EB over A, which is this one, decreases slowly. Oh, I need to correct this one. Decreases slowly, indicating that the nucleons are on average less tightly bound. Okay, so this part here, they are not it's not that stable in comparison to this one here. Okay, so for heavy nuclei with A between 200 to 240, the binding energy is between 7.5 and 8. These nuclei are unstable. This nuclei, the nucleus for this what do we call this element, are not that stable, are unstable and radioactive. Okay, and then this figure pula, it shows a graph of neutron number against the atomic number for a number of stable nuclei. So the stable nuclei are represented by the blue dots, which is the one shown here, which lie in a narrow range called the line of stability. So this is the dashed line correspond to the condition n equal to z. This is basically the line of stability lah. Okay, so the light stable nuclei contains an equal amount of number of protons and neutrons, which is what is written here. But in heavy stable nuclei, the number of neutrons is always greater than the number of protons. Okay, so the line of stability deviates upward for different atomic number lah. Okay, so as the number of protons increase, the strength of repulsive Coulomb force increases, which tends to break the nucleus apart. Okay, so because of that, more neutrons are needed to keep the nucleus stable, because it will only experience an attractive nuclear force. Okay, so if in exam they ask you to draw a graph, you just basically have to draw something like this. Okay, that is on our first subtopic.